Fair warning. Be loud. Okay. So chapter 5, we talked about a special type of discrete distribution, which we knew as the binomial distribution. Then we talked about how to find the associated probabilities by hand and on the calculator and using the table. This chapter, we talked about a special type of continuous distribution. It's known as the normal distribution. So it pops up in various applications all across the world and all across disciplines. So what does it say? Recall the definition of a probability distribution. We need to somehow list all the possible outcomes a random variable can obtain and their corresponding probabilities. However, for a continuous random variable, there's an infinite number of values it can take. So you can't list out an infinite number of values. So therefore, we use what is called the normal distribution. Sorry, I'm hungry. I haven't ate yet. I didn't go to bed till 2 o'clock. I was very, very tired when I woke up. So instead, we will draw a curve that presents all the possible outcomes the random variable can take on. So what does it look like? Something like this. So it looks like a bell. And then what goes where? So the x-axis is where all the possible outcomes will go. And then the probabilities will be associated by the area under the curve up to some value. So it talks about many continuous random variables tend to have probability distributions that are bell-shaped and symmetric, i.e., it looks like that. We say these variables are approximately normally distributed. So in this chapter, we'll focus on drawing normal distribution curves. So then it says the next part, well, it has a graph, and all it says basically is here is the x-axis. So this is the possible outcomes you could have for your random variable. Here is what we'll denote as the mean, so the center of it. And then we're going to be interested in what's the probability of getting something, say right here, as our mean, as our sample mean. The shape of these curves will be defined by the mu, so where is the center of it? And sigma, what is sigma? Standard deviation. It'll tell us how spread out or how elongated the curve will be. Now, let's talk about some specific properties of it. So you will need to know some of these for your homework. It's the first question. The first one says the curve is bell-shaped, so it just means that. Number 2, it relates to the measure of central tendency, the mean, the median, and the mode. Are what? Are all equal and located at the center. What does that mean? The center of the curve is here with some mean mu, and also you could say this is the median or the mode, either one. So whenever I ask a question on the exam, it says I have a normally distributed random variable, and I tell you the mean or the median or the mode, you should be able to determine what is the other 2 of them. It's just equal, that's all it is. Next thing, the curve is unimodal. 4, the curve is symmetric about the mean. What does that mean? What is symmetric? Symmetric means if I take a line at this mean here, and I reflect it across that line, I get the same thing. Then, since it's symmetric, that means what we'll say is an equal probability or equal area lies below the mean and above the mean. We'll expand this later when we talk about finding the area between two of them. The next thing it says that I just dropped the mic. No, I did not. The curve is continuous, so no gaps or holes. So you know what a hole is, right? There's a hole in the graph. In the normal distribution, that doesn't happen. The next thing, you'll need to know this, the curve never touches the x-axis. Theoretically, it can take on an infinite number of values, so it will never touch. Probability of 0. What was that number? It was 6. What's the next one? The total area under the curve is 1% or 1 or 100%. Why is that? A total probability should add up to what? 1, and probability is measured by what in this case? The area under the curve. So the total area should be 1. And this last thing we'll talk about is what is known as the empirical rule. I guess first I'll mention number 1 on your homework goes over this exact definition. And a lot of people mess it up. Let's look at what it says. I'm going to actually flip this around so you can see. 1 or 100%, not 1%, my bad. So we'll go over here. It says, which the following are characteristics of normal distribution? So all I want you to do is select the ones that are properties of it, just like we set up here. Let's figure out which ones. A normal distribution curve is bell-shaped. Obviously, that's true. So that's one of them. The mean, median, and mode are all located at the center. That's one of them. The normal curve is a discrete distribution. Is it? No. It's false. It's continuous. So no, not that one. The area under the part of the normal curve that lies within 2 standard deviations of the mean is approximately 95%. That is actually true. We'll talk about that in a second. That is the empirical rule. The area under the curve, that's false. This one's true. That's empirical rule again. So the normal distribution curve is unimodal. That just means there's one mode or one peak. That is true. We said that in the definition or in the properties. The normal curve is symmetric about the standard deviation. That doesn't make any sense. Symmetric about the mean. The normal curve crosses the x-axis. That is no, it never crosses the x-axis. And the last one, the total area under the curve is 1. That's right too. Uh-oh. Someone's getting a call or a FaceTime.
I have to go down to North Dining for coffee. I have to pick it up. Is it cold?
Yeah, it's very cold. That was great. Grab me a coffee while you're there. I don't like coffee. Oh, gross. That's a little zoomed in. I'll zoom out. Well, it's recorded, so that'll be on YouTube. Let's go back here. Next thing we'll talk about is the empirical rule. Someone else unmuted? Where's the mute all button again? Participants. You are the best. Mute all. Yes. Ta-da. There we go. Holy cow, there's like 26 people online. Did no one want to get out in the cold? It is freezing. Me too. I forgot my beanie. I was kind of mad. Fair warning, I can't draw very well. I will try my best. So at the middle, there's the main mu. What this first rule says, approximately 68% will fall within one. That is way too small. Wait, that's fine. With one standard deviation of the mean. So you have mu minus sigma, mu plus sigma. So the probability of it lying within this region right here is 68%. So that'll look like this. Okay, that was not a straight line, but that's okay. The area in here is a whopping 68%. That's what the first one says. Then the second one. Within 2 standard deviations, so we go out to mu minus 2 sigma and then up to mu plus 2 sigma. If we look at the area in between these two boundaries, so there's a color on besides that. The area in between these two, including the middle, so that includes this area here too. All of this is 95%. We'll talk about why that is later. And the final one, I have another color in here somewhere. Do we want, where's the colors at? Put new colors in here. Do we want brown or magenta? Magenta, got it. Then within 3 standard deviations, so mu, that is ugly, mu minus 3 sigma to mu plus 3 sigma. So within that region here, so it's all of this. In that region here, there is 99.7% of the data values will fall within that. And that is for a normally distributed random variable. Then what in the world does that mean and how do we apply it? There's an example on the next page on how to use it. It says using the empirical rules, solve the following problems for a normal distribution with mean of 80 and standard deviation of 10. In that case, what is mu and what is sigma? Yep, mu 80. So we have a mean of 80 and a standard deviation of 10. What does the first one say? What percentage of values will fall between 60 and 100? So we need to figure out which one of these is it. 60 is equal to 80 minus 2 times 10, right? And 100 is equal to what? 80 plus 2 times 10. That means it's within 2 standard deviations of the mean. So it's this one right here. Therefore, 95% of the data values fall below those 2 boundaries of 60 and 100. Everyone understand why that is? Just using that, what rule is it? The second one? Yeah, second one. The next one. What percentage of values will fall below 70? 70 is what away from the mean? So if we have 70 equals 80, it's obviously minus 1 times 10. That means we're 1 standard deviation away from the mean on this side. So we're right there. Now, how in the world do we solve this? Notice that 68% of the data is within this region here, right? No. Then, since 68% is in between these two, what is the percentage left in these two regions added together? 100 minus 62 or 68 is what? 32. So there's 32% remaining outside the interval of mu minus sigma to mu plus sigma. That just means the area outside of this region here is 32%. Why? The total area has to add up to what under the curve? 100% or 1. Then you just take the area we have here, and to find the area outside of it, you subtract it from 1. Does that make sense? Now, since the distribution is symmetric about the mean, so that means an equal probability lies below the mean as above the mean, then the area of this region here is equal to the area of this region here. Does that make sense? Is it kind of confusing? Yeah, it is. Let's think of it this way. Trying to think of how to explain this. As long as you are the same number of standard deviations away from the mean on both sides, then the area outside of those will be the same. That's, I guess, another way to put it. I'll explain why that is with your table in a second. It's kind of confusing. That means, so we have 32% is outside this, right? So an equal number or an equal percentage is distributed in this one and this one. So to find the area in just this one, what do? Divide by 2. That means that 16% or 0.16 is below 70. There's a numerical way, we'll show that later. It'll be a lot easier to do, and you can use your calculator to find it. Then the last one says, within what boundaries does 68% of the data values lie? That's just using the first one, but 68% will fall within 1 standard deviation of the mean. So what is the boundaries there? 80 minus 10 is what? 70, and 80 plus 10 is what? So within these two boundaries here will be 68% of the data values. Every time, are you going to get something that is exactly 1 standard deviation, 2 standard deviations, or 3 standard deviations from the mean? The answer is no. Was the last one 10.16 or? Oh, this is an implied sign. It's just 0.16. So that was the answer to B, and then the answer to C was 70 to 90. It's just 1 standard deviation from the mean. So you take mu, which is 80, subtract off 1 times 10, and then add 1 times 10. Have I confused everyone? I probably have. Fair warning, it's just going to get worse. It'll get a little bit easier though. Remember that the area under the normal curve represents the probability, and the empirical rule only tells us what happens for 1, 2, and 3 standard deviations away from the mean. So that's not very general enough. So what we need to do now is define what is called a z-score. The z-score represents the number of standard deviations that value or that data value is away from the mean. In this case, whenever we looked at this, we were interested in what is a z-score of what? We just looked at 1, 2, and 3 standard deviations from the mean. So you just say plus or minus 1, plus or minus 2, and plus or minus 3. So that's what we dealt with here. Now, we need to generalize this more. So it says for sample data, we will define the z-score to be, I'll write it right here. So for sample data, you have the z-score is equal to what? You take the data value you're interested in, little x, you subtract off the mean, and you divide by its corresponding standard deviation. So here, x, the little x is the data value you're interested in. X bar is the sample mean. And S is what? Yeah, sample standard deviation. If you want to use a population, then what happens? What do you think? If we have population data, then you know the population mean and the population standard deviation. So the only thing that changes is becomes x minus mu over sigma. So here, x is still some data value you're interested in. Mu is the population mean. And sigma is what? The population standard deviation. So that's what you'll use to find a z-score. So what in the world do you use it for? We'll talk about that in a second. Now, there's 3 different scenarios of a z-score. It could be positive, negative, or 0. If it's negative, what do you think that means about the data value relative to the mean? Standard deviation is always what? Positive or negative? Positive. It's the square root of the variance, and the variance is always positive. That means that this quantity here will always be positive. If z, so this whole thing is negative, then that means this numerator must be negative, right? So what does that mean? That this value right here must be smaller than this one, right? If z is negative, then the data value x falls below the mean. And that should make sense. If this value here is smaller than this one, I'm subtracting a larger value from a smaller value, so it's negative. Then I'm dividing by a positive value, so it doesn't change the sign. If z is positive, then using that same idea, what is x relative to the mean? Yeah, above, because then this would become greater than this, and it becomes positive. So if x is above, if z is positive, x falls above the mean. I'm not saying sample or population because it's the same for each case. And the last one says, if z is 0, then the only way that can happen is if this numerator equals 0. And if that happens, the data value is the mean. That makes sense why that is. How many people are confused? I love the honesty. Yeah, so if it's equal to 0, remember that this s right here is positive. So the only way that can happen is if x minus x bar is equal to 0. So that just means the data value we're interested in is actually equal to the mean. That makes sense? Someone online is confused too. Don't worry, you will be for a little bit until we do an example to illustrate what in the world we're talking about. Yeah, if you've never seen this before, you're gonna be like, what the heck? Yeah, it'll happen. Now, it says, for example, say you score a 96 on your first stat test. So a lot of people did that. Some people did better. And a 71 on your first history test. If you wish to compare these scores, they first need to be standardized in order to make comparisons. Why do you think that is? Are a stat exam and a history exam equally as hard? No. To me, a stat exam is easier than a history exam, but to you, it may be the other way around. I didn't like history. So then it says if the mean score on the stat test was an 82 with a standard deviation of 10, and the mean score on the history test was a 62 with a standard deviation of 5, then we can calculate the z-scores for each of these and then compare those to see how you did relative to everyone else in the class. Does that make sense? Then, first thing, find the stat z-score. What the heck does that mean? Make a column that summarizes all the stuff you know about the statistics, mean and standard deviation. So what is the actual data value in this question? It's the value you got on the exam, which is a 96. So little x, and our problem is 96. It says the mean of the statistics exam was a what? 82. So that means mu is 82. Or you can say x bar, either way, it doesn't matter. And the standard deviation was what? 10. So then you can plug it in to this one right here. You know what the data value is, you know what the mean is, you know its corresponding standard deviation. Then the z-score for your stat test is equal to what? Just using that formula over there, you take the data value, 96, you subtract off the mean of 82, and you divide by 10. If you do that, what do you get? 14 over 10 or 1.4. What does that mean? On the stat exam, you performed 1.4 standard deviations above the mean. Basically, you just scored 14 points higher than everyone else on average. And the history one, you want to do the same thing. What was your history score? What does it say? 71. The mean of it was what? 62. And the standard deviation was what? 5. Then computing that z-score, you get what? Z is equal to 71 minus 60. Oops, that's not a 6. Minus 62 over 5. What does that give you? 9 divided by 5 is 1.8. Oh. That means on your history exam, you scored 1.8 standard deviations above the mean. And why am I saying above the mean? Because your z-score is what? Positive. So that means this part here is positive. What in the world does that mean? What's up? I just told, it really doesn't matter in this case. If you want to be picky, if I say sample data in the problem, then you can use the sample one. If I say population, you can use population. You'll get the same thing either way. Because it's the same idea. You take the data value minus the mean, divide by the standard deviation. Then comparing these two z-scores, which one is larger? 1.8 or 1.4? Obviously, 1.8 is greater than 1.4. What does that mean? Yeah, you did relatively better on the history exam than on the stat exam. Would you like me to write that on the board? Awesome, great. Now the next part says, remember, z-scores represent the number of standard deviations each value is from the mean, and above or below is indicated by the sign in front of it. So therefore, using the z-score for your statistics exam of 1.4, that means you scored 1.4 standard deviations above the mean. Now, the next part, I really hate doing this part. When we standardize all values of x, we transform our distribution to have a mean of 0 and a standard deviation of 1. And we call this distribution the standard normal distribution. That means that these z values we're talking about, they have a distribution and they're distributed normally with a mean of 0 and a variance and standard deviation of 1. I don't need to do that part. It's just the same as earlier. I guess I'll show it to you. Here. So what is it saying? You take some distribution here. X is the outcomes it could take on. Mu is the population mean, and sigma is the corresponding standard deviation. So sigma and mu can take on any two values depending on what you're dealing with. But whenever you standardize them using this formula above, wherever it is, those two, then the distribution becomes the z distribution, so the standard normal, that thing. And it has a mean of 0, so that means the middle of it is at 0. And the standard deviation, which is the spread of it, can be measured by 1. Why do you do that? Because you have a table for it. Is there another way to do it? Yeah, we'll show you. It's the calculator. It's a lot easier. That's the same thing. Just as in chapter 5, we wish to calculate certain probabilities of our random variables. But before we get to calculating the probabilities, let's focus on calculating probabilities of z-scores using the standard normal table. What in the world does that mean? So your standard normal table will tell you, based on the z-score, what's the probability that it falls below that z-score? What was the key thing that I said there? If you have the z-score, you can find the probability. later, we'll talk about whenever you just have data values. So I give you the sample mean, I tell you some value you're interested in, and then you find the number of z-scores it is from the mean, just like that. So let's look at what it says. The first step, draw the normal curve and shade the appropriate region. What in the world does that mean? So let's say I say, find the probability of z being less than or equal to 1. So here you have a z distribution with a mean of 0. And I'm saying find the probability that z is less than or equal to 1. So then I have some z-score here, 1, and I'm interested in what area. Less than or equal to is what? Less than or equal to is this left-hand area, right? Oh, I'm not even showing it on the board. Whoops. There you go. If I say find the probability of getting a z-score less than or equal to 1, this is what the actual region I'm interested in finding the probability of. Now there's two ways you can do this. You can use your calculator to find it, and it's a little bit easier, or you can use the table. I'll show you how to do both. If I brought the tables, I think I did. Can anyone guess which table you will use? It does the standard normal table on it, so you use that one. Where is it? So it's on page 7 of your distribution tables packet. That's on Canvas. So what does this table look like? This thing. Let me change it back to the document camera. Here, it has z. So this is the z-score you're interested in. And it has the first 2 decimals. So it has whether it's 1, 2, 3. Then it also has the 10th digit here. And then above the top here is the second digit. So the ones or whatever it's called. Yeah, the tenths and the ones. Yeah. In this case, I said find the probability of z being less than or equal to 1. That means I will go first along this part here to where z is 1.0. And then I will go to the tens place or the ones place. And there is no ones place here in this problem. So then the probability to the left of it is just this one right here, 0.8413. This next example is not your notes, I just made it up. So if I tell you that's the area to the left of that, what is the area to the right? 1 minus that. So the area to the left is just the complement of the area to the right. Does that make sense? Because the total area under the curve should add up to what? 1, since the probability distribution. And if I tell you the probability of the left, the opposite of the left is the right. So therefore, those two areas should add up to 1. Now look at the next example in your notes. What does it say? Find the probability of z being less than 1.20. If someone has your distribution table, tell me what that answer is. All you do is look for 1.2 on the right, on the left-hand side, and then 0.00 on the top. What'd you say? Yep, that's right. 0.8849. all you do is do 1.2 and then intersect it with 0.00. That's 0.8849. Does it matter if I put less than or equal to? So for a continuous random variable, it does not. The probability of it can take on any specific value for a continuous random variable is, what do you think? 0. Can anyone tell me why? Probability for this example is measured by what under the curve? We talked about at the very beginning. Probability is measured by the area, right? Area for a rectangle is what? Length times width, right? If I'm looking at the probability of any one particular outcome, then I'm just having a vertical line up to that on the curve at the particular value I'm looking at. What is the width of that line? There's no width. So therefore, there's no area. What is, you want me to draw it out? Okay, I'll draw it out because I'm confusing the heck out of all y'all. I say, what is the probability of, here's the mean of the standard normal and here. Say this is 1.2. I want, what's the probability of z equaling 1.20? Now, remember that the area is the probability in this case under the curve. And area for a rectangle is equal to length times width. Yes, sorry. Gosh dang it. That is the one bad part about Zoom. I'll forget about half the time. There you go. So we're on this thing. I'm saying, what is the probability of z equaling 1.2? So if it equals 1.2, that's just a line up to the curve where it hits. Now, remember that the area for a continuous distribution is equal to the probability. Now I'm using the fact that the area, so say for instance, I was looking at here and I said, find the probability of z being less than or equal to negative 1.20. That's all that area right there, right? I can approximate that using rectangles. And then I can take all the area of those rectangles and add them up. This is getting a lot more theoretical than I wanted, but I'm trying to explain. Then, using that same idea here, I'm only interested in what's the probability of z being this one particular value. Now, so the length of this line, it has length. It goes up to the curve at where it crosses. But what is the width? Since it's just a vertical line, there is no width here. So this width is equal to 0. So the area of just this line segment is equal to 0. Therefore, the probability is equal to 0. Did that make sense at all? Oh my Lord. Just remember this. For a continuous distribution, the probability of any one single outcome is 0. Remember that rule. That will guaranteed show up. Now, someone do the number 2 on the examples. What's the probability of z being less than or equal to negative 2.24? Someone besides Grace answer. See, I know some people's names now. Let me check. I'm pretty sure that's right. No, I don't want the emojis on the screen. What'd you say? Excellent. That is correct. You're just looking at the area to the left because it's less than or equal to. And the chart will tell you that already. So you don't got to worry about doing 1 minus it. Now the next one. It says, what's the probability of z being greater than 2.11? Then for this right here at the bottom, gosh dang it, I got to switch it again. Here, this bottom one, say you have your mean of 0 here, and you have 2.11 is up here. What area are you interested in this case? When z is greater than 2.11, so it's this area to the right. Correct? But your table only tells you the area to the left. What do you do to find the area to the right? Mistake 1 minus the area to the left. So find this area here first. Find all of this. And how do you do that? You just look up the probability of z being less than or equal to 2.11. And that'll tell you all the area to the left here. So all of this, all that. And then to find the area to the right, you just take 1 minus the area to the left. So what's the area to the left of 2.11? If I look in the table and intersect 2.1 and 0.01, I get this area here is equal to 0.9826. And that's the area to the left of z being this. If I want the area to the right, then I need to take 1 minus that area to get the area over here. There's 1 minus 0.9826, and that gives you what? 0.0174. Would you like to see an easier way to do this than besides on the tables? Let me show you. Last chapter, we did the distribution thing on the calculator, right? For a binomial. You can do the same thing for a normal. And to do that, you hit second vars. So a normal PDF will tell you the area accumulated up to some z-score or up to some data value that you're interested in. This, well, I'm trying to think of how I want to say this. Yeah, just use the normal PDF for now. We'll talk about the CDF later. Now, hit normal PDF here. So the X value. So in this case, we're just dealing with z-scores. So put the z-score here. 2.11 is the one we're looking at. The mean of the standard normal is 0. The variance is 1. To find the area, I just go down, hit paste, hit enter. What in the world? Normal PDF. Did I hit the right thing? 0.043, blah, 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 blah. That makes no sense. We're going to do something else. Yep, I hit the wrong thing, that's why. Do normal CDF. I was like, I know something's wrong. This will tell you the lower boundary of the distribution, or the lower boundary you're looking at. So just leave it as -1E99. That just means a large negative number. So that's just going to take this all the way out here, all the way to the very end, the theoretical end. And then you want to tell it what's the upper boundary. So you're looking at the upper boundary in this case was 2.11. Oops. There. Then if you do that, hit paste and then hit it, that'll tell you the area to the left, which is what we got there. And then you take 1 minus that to find the area to the right. You can do the area to the right as well. I'll show you in a second. How to do on a TI-83. In the TI-83 case, you will literally just do this order here. So you go to normal CDF, you enter in the lower boundary. So all you do is hit -1 and then go second comma, and that'll do E. And then you do 99. And then you put a comma, and then you put the Z-score you're interested in. Or in this case, you could do the data value if you wanted to. Then you tell it the mean, and you tell it the standard deviation. Do you want me to write that on the board? How you do it? Okay, I'll do that. If you have a TI-84, it just lets you enter it in. But if you have the 83, then you have to do it. Kind of a pain in the butt. Oh, I need to turn the camera around again. Gosh dang it. It is just a hot mess today. So do normal CDF -1 E to the 99, 2.11, 0, and 1. If you want the more general form, then this is the lower cutoff you're looking at. This is the higher. This is the mean. And this is your standard deviation. Can you change this to where it just doesn't deal with Z-scores? Say you have any normally distributed random variable, you know the mean and you know the standard deviation, you're interested in what's the probability of it being some particular value or being less than or equal to some particular value. Then you can just plug in the numbers here, changing the mean and the standard deviation. You tell it the lower value you want it to take, and you tell it the upper, and it will find the probability. That way you don't have to find the Z-score and then use that in the table to find it. Is it a little bit easier on the calculator or not? Okay. Now, what's the next one say? Is this the one in between? No, don't worry about that next one. We'll talk about this number 5 on your notes. I'm going to write it on the board. Where'd my black marker go? There it is. It says, what is the probability of Z being between -1.5 and 2.12? We'll just draw a new one. It says 1.5 and 2.12, right? Then if I draw the standard normal curve, here is the mean of 0. Here is, say, -1.50. And here is 2.12. What area do I want in this case? This one, or this one? What do you think? If I want the probability of it being between these two, I obviously want the area in the middle. So I want this. How do I find it? The table will only tell you the area to the left. So therefore, I can look at the probability of it being less than or equal to the upper boundary of 2.12. And that'll give me all the area from here all the way until the end. But I only want the area up to negative 1.5. How do I get it? Just subtract off the area to the left of this. If I do that, then it will give me the area in between the two. So therefore, this is equal to the probability of z being less than or equal to 2.12 minus the probability of z being less than or equal to negative 1.50. I guess it doesn't matter if you put these in here. What's this first one? The probability of z being less than or equal to 2.20 or 2.12. If you look it up in the table, it is 2.12.9830. You want me to show you how I did that? Okay, let's turn the camera again. All you do is zoom a little bit. 2.1 on the left-hand side, and it says 2.12. So we're going to look at 0.02 up top, and then we'll intersect those two. And if I do that, I get 0.9830. So that is this part right here. 0.9830. Now, to find the remaining part, I need to look at what's the probability of z being less than or equal to negative 1.50. That'll be on the previous page. Then here I'll go on the left to negative 1.5. And since it's 0.50, I just go 0.00. And I get 0.0668. What is the difference between those two? Yeah, 0.9162. Is there an easier way to do it instead of looking those up on the table? There is. So, yeah, tell it the lower boundary, tell it the upper boundary. In this case, the lower is negative 1.5. The upper is 2.12. The standard deviation and the mean, respectively, are 0 and 1. Because you're still dealing with the z-scores. Oh my lord, there's a lot of this chapter. Don't forget I have office hours if you need help. No one comes by to sit in my office. Now, let's look at the last one. The probability of z being in between 0.54 and 2.33. When are your office hours again? Tuesday, Thursday, 3 to 4, and Monday on Zoom. From what time is it? I don't know. No one got on them, so I haven't got on them. I just haven't got on. It's on an email or something. I don't know. Oh, wait, it's on the updated syllabus. I think it's 4 to 5 or something like that. Did anyone figure out the answer to number 6? Yep, correct. using that same idea, you just look at what's the probability of z being less than, and instead of this case, this would be 2.33. And this one would be 0.54. You could also enter it in the calculator using this and replacing this lower one by 0.54, this upper one by 2.33. The mean is 0, the standard deviation is 1. And it will give you basically the same thing. Your calculator gives you an exact answer. The table rounds to 4 decimal places, so it may be off in the 4th decimal. Would you like me to look at an example from your homework to make it a little bit easier? Let's look at one. Where in the world did I put it? Trust me, it'll get better once you practice. Here we go. Where is one that I want to do? Let's look at this. This is number 8 on your homework. Find the probability using the standard normal distribution, the probability of z being in between negative 2.29 and 2.48. Using that same idea we have, you can find this by the probability of z being less than 2.48 minus the probability of z being less than negative 2.29. Let's look at this first probability here. And the probability of z being less than 2.48. If you look up that on your standard normal distribution table, you will get 2.9934. So 0.9934. Then if you look up this one, negative 2.29, you will get 0.0110. Wait, that was wrong. What did I read off? Yeah, 0.0110. So then to find the area in between, you just take the subtraction of those two and you get 0.99, oh shoot, wrong button. 0.9934 minus 0.011, 0.9284. Then the idea is if you're looking at a z-score being between two values, take the probability of it being less than the upper and subtract off the probability of it being less than the lower, and that'll give you the area in between. Oh, some other people said some stuff. What did they say? Okay, never mind. Now, let's look at, should I look at another one or not? Okay, cool. The other two are basically the same thing. The next thing we'll talk about is what? Now, what if we were given the probability and asked to find a corresponding z-score? Can anyone tell me what that would look like? I tell you the area, say, I tell you the area to the left of some z-score here. I tell you all this stuff. Can you find what this value should be? And the answer is yes. How would you do it? So I'm giving you the probability already, so you know what this is. Say it's like 0.9824. I have no idea if that number's in there, by the way. I tell you this area to the left here. You should be able to look inside this table here. So this gives you all the areas to the left. all you need to do is look in the table for this to find that associated z-score. Let's see if there's actually one that has that. 0.9824. 0.98. Okay, we're pretty close. 0.9821 and 0.9826. So it's probably around 2.1005. Probably in between those two. Can you find the exact one? Yes. And how will you do that? Just thinking again. Now, hit second vars. So like how the normal CDF would tell you the area accumulated up to something, if you hit inverse norm, that'll tell you the corresponding z-score or data value that you have associated to some probability. So hit inverse norm, you tell it the area. So in this case, it was 0.9824. 9824. You tell it the mean. So in this case, we're still dealing with just z-scores. So the mean is 0 and the standard deviation is 1. You tell it which tail is that probability in. This probability is in the left tail because the area to the left. Then hit paste. Then it tells you the exact z-score. 2.106. That was pretty dang close. Just guessing. That is the idea behind this section. I give you the probability. I want you to find the associated z-score. What's up? It'll give you it'll be automatically to the left. So if it tells you the area to the right, say for instance, if I told you the area to the right was 0. Whatever the right of this is, 0.1176. If I told you this area is the area to the right, all you need to do is find the area to the left because that's the default what your calculator will give you. So in this case, I already gave you the area to the left. So all you do is enter this in. Yes. Yes. If you have that newer 84, you have the option to change it to the right or two-tailed. Does it give you the option for two-tailed? Crap, wrong button. That's inverse T. We don't do that. I guess you could. Yeah. So yeah, it's either left or right. We're not going to worry about the center. Then using that idea, look at the first example. What is the let's look at the second. We just did something like the first. The probability of z being greater than the unknown z-score. So little z here is the unknown z-score. This is unknown. It's saying what is find the probability of z being greater than some z-score is 0.0136. That is saying that the area to the right of some z-score here, the area to the right of it here is 0.0136. But the table only gives you the area to the left. So what I want to first do is find the area to the left of this. And that will be 0.9164. Is that right? 0.9864. I'll check my notes. Yes, 0.9864. That means I need to look for a z-score such that the probability of z, the random variable, being less than or equal to this unknown z-score here is equal to 0.9864. If I look in the standard normal table, I should find a value with that area to the left. And what is that corresponding value? I just saw it a second ago. There it is. Anyone find it yet? Besides Grace? Yep, correct. If you do that, just look for 0.9864 right here, 2.2 up to 01, so 2.21 is the z-score associated with that. That implies that the little z we're looking at, the unknown one, is 2.21. Did everyone understand how I did that? Okay. Let's look at the next one. Okay, that's the same idea. This one is fun. You will get confused. I will tell you how to not get confused. The probability of negative z to positive z being 0.866, is that 2 6s? 8664. That means the area in between a negative z and a positive z is equal to 0.8664, correct? Then I can find the area outside of these regions by what? Just 1 minus that, correct? If I do that, 1 minus 0.8664 gives me what? 0.1336. That means the area in these two tails here added together give me this. Yeah, split it in half. Split that in half, and it will tell you that half of this area is going to lie here, and half of the area will lie there. So if I split this in half, what is that? 0.0668. That means the area to the left of this negative z-score is 0.0668. Then I can just look for that. So the probability of getting a z-score less than or equal to this negative z value is equal to 0.0668. If I look for that z-score in the table, I should be able to find it. And what is it? 0.0668. Where's that? Yeah, right here. Negative. Actually, I looked at the wrong one. What did you say? I'm pretty sure that's right. Yep, positive and negative 1.5. So it's right here, that one. So that implies that this negative z is equal to negative 1.5. So the positive and negative z-scores that were unknown are positive and negative 1.50. Then using that same idea here, you can find the corresponding z-score by taking 1 minus this area here, dividing that by 2, and that'll tell you the area to the left of this negative z. And then you should be able to figure out that the positive and the negative z-score of that is equal to positive and negative 1.74. Hopefully I didn't confuse you too much.